Hi. In this video, I will be going through the second walkthrough for the mysh CSC209 project. My name is Aarav Pradhan, and I will be continuing demoing all the new features that have been added after milestone 5. To start off, I would like to show that the code compiles properly when make is ran, and that the executables are created without any forms of errors or flags. First, I will perform a make clean to show that I'm removing any other executable files or anything that is currently present in the directory. Then I will check the directory. There are only source files present in the directory and no other files, and also there is a make file present. Next, I will be running the make command. And as visible here, there are no errors present. Now that we've shown that the code compiles correctly, I will now be providing some examples of how background processes work, including how the signals are sent and explaining in a very brief manner how those work. I will also be showing how processes are listed using the PS command that I have built in coded, and I'll be demoing those processes for you. Starting off, I will run the mysh executable, and now I'm in the mysh shell. To start off, I will show a simple example of a background process, such as echo hello, and I will be putting an and after that. As visible here, there is a there's a job number, which is job number 1, and a PID that is assigned to this particular process. And once the process is done, it prints it on the shell, and a done message is printed right after that. And then it returns back to the shell for me to perform any other commands. I will also be showing how a process is listed. First, I will show this. It's using the command sleep 100. And I'll be putting a background process by the ampersand at the end. And when I run this, it'll be providing me with the job number and the PID related to it. And now to show that this has been listed in the process listing, I'll run ps, which is my built-in command. And as visible here, the command sleep 100 is present with the same PID as the command that I had ran, thus showing that this works correctly. Now, if I would like to kill this command, I can write kill and I can put the PID right after it, and my command will kill the sleep command, and it prints the done message, which is +1, which is a job number, done sleep 100, which is the command that I had killed. To show that there are no commands now, left in the process listing, if I run ps, then nothing prints, which is as expected. Furthermore, to prove that when multiple background processes are occurring, the processes are listed correctly, I will be running 2 sleep commands concurrently. I'll be printing sleep 100 and then putting an ampersand to show that it's a background process. And I will be also putting another sleep 200 with an ampersand after it. And these have the job numbers 1 and 2 respectively, and the following PIDs. Now to show that the processes are listed correctly, if I run the ps command, the first command that shows up is sleep 200, which is my most recent command with the matching PID as expected, and then sleep 100, which has the PID of 470995, which matches the one that came up here. Now to cover the aspects of signal handling. To start off, I would like to first show how the process of Control C being pressed inside the mysh shell does nothing as expected as intended. This is done by first putting inside the main function a struct of type sig action and setting the signal handler to sigint handler. As visible here, inside the sigint handler, nothing is performed, which is the intended functionality. When sigint is sent, or the signal of interrupt is sent to the mysh shell, then the sigint handler is called, and it just performs a display message and does nothing else of the sort. And the usual performance of the sigint handler the default performance would be to end the process, which is not happening here, and instead it's just displaying the next message. Furthermore, in the implementation of background processes, we are creating a fork that allows the child process to run in the background of the program, while the foreground of the program performs regularly like the mysh shell. To detect when these background processes are done, a sig action struct is created that detects any sig childs. The sig child in this case is when there is a change in status of any child process of the parent process in this case, which is the mysh shell or main. As visible here, inside sig child handler, nothing else except the check jobs function is called. Now I will be covering the check jobs function, which is responsible for printing the appropriate done messages and the interaction with inputs from the console. Now, once the check jobs function is called by the sig child handler, it loops through the list of background processes that are present. And these background processes are stored in a linked list-like structure in the mysh code. And as it loops through, it checks, it performs a wait PID, which has a non-blocking stage, which makes sure that there isn't that the code does not stop running and wait until this process is done. But it checks for the status of the code, whether it has is terminated or it has stopped working or there is an error. And if in the case that there is a termination status or that there is an error, the result or the value returned by wait PID would be greater than 0, which would allow for this the job to be outputted as done. So once this is indicated that the job is done, then it prints the done message using the display message function, and it updates the list of jobs or the linked list structure to remove the background process or job that was present before so that it also updates when PS is called. Furthermore, to discuss how this interacts with input from the console, what happens is that the display message prints the standard output and it goes to the next, it prints a new line right before the done message, which means that the user input isn't interrupted or blocked. And since it is displaying the standard output, the standard input buffer won't actually be interfered with. So whatever the user might be entering in the console at that moment won't be interrupted. Also, since it uses a SIGCHILD handler, it interrupts the current process or the shell, prints the done message and returns back to the shell, making sure that everything that was there before is preserved. And lastly, to examine the relationship between user input and the done messages in the shell, when a user inputs a kill command for a particular PID of a background process, then the background process is terminated and that sends a SIGCHILD, and the SIGCHILD handler, which I have coded before and shown previously, will then call the checkjobs function, which prints the done message if that process is if that process in particular is done. This shows the relationship between how the user input and the done messages are called, and then the done message returns and it goes back to the shell. An alternative approach to using the checkjobs function paired with a SIGCHILD handler is to simply use a function that is similar to the checkjobs function inside the mysh loop. This would mean that inside the main function, as every iteration of the mysh shell continues, which waits for the user input, it also first checks whether any jobs are completed inside the background process list or any other storage methodology used by a person. If in the case that it is, a done message is printed. However, the reason I had personally chosen not to use this methodology or this idea was that it is dependent on a person continuing to press enter or go to the next line of the myset shell, as the loop only continues once a user has put an input. This means that if a job is completed during the time a user is inputting something, it won't immediately print the done message, which would mean that there would be a delay in the time that a background process is actually represented as done. This would cause issues with the accuracy of how PS works or background processes are reviewed, and that wouldn't be a very efficient or useful approach. Now for a high-level overview of how the server handles messages that are received from the client, and specifically covering the case where the message from the client is too long. For a brief overview, this code represents the beginning of the server handling client messages. And for a very brief description, it loops through all the connected clients that are stored inside the mysh shell. And it checks whether there's any data present in the socket. In the case that there is, it begins to process that information or process the message to then print out on the chat server and to send back as feedback to the client that sent it and to any other clients that are connected to the same server. Specifically to cover the case where the message is too long, what happens is an if condition is present that checks whether the length of the message that is received or sent by the client is longer than the restricted length, which is a value that I have set to a macro. In this case, is 128 characters, and what it does is if in the case that it is longer than the restricted value or restricted amount, then it first truncates the message, and it also notifies or sends a message to the client of a truncation or that the message has been truncated to these many characters, and it also sends the feedback to the client of the corrected message. So what happens here is that the truncated message is then sent to the server, is printed by the server and the clients and any clients connected. And the next time the client sends another message through their socket, the remaining amount or the remaining message will end up being printed. So what happens here is that the truncated message is printed by the client or echoing back to the sender, and then is printed to the server console and is also broadcasted to any other clients. And the next time the loop continues, and it checks whether the client has sent any more information or the socket contains any data, then it prints the remaining information. When covering the pros and cons of this approach, I think the biggest benefit of this approach is that when a client sends a message, eventually all the data that the client intended to send will be sent to both the server and any other connected clients. This ensures that there is no undefined or unexpected behavior when a client sends a message, as they might not be aware of the size limit or the size restriction of the message that is sent. This ensures that there isn't data loss or that there's extra data that is just being left without being displayed or sent to any of the client's servers, which is overall a beneficial approach. However, a con of this approach is that it is dependent on the client sending another message, as the remaining message that after truncation is left over will only be sent when that same client who sent the oversized message sends another one, and that has to also be less than the length of the restricted amount. This would mean that when you send an oversized message, only half of it would be sent, and the remaining may or may not be sent depending on whether the client continues to talk. And that concludes this final walkthrough of the MySHC presentation. Thank you.